Okay, so I had some technical difficulties earlier today, so you can't see me, but hopefully you can hear me. I'm going to go through and explain finding a derivative for you. This was what we have just been doing. This quick slide is just showing you, we took the x plus h and we substituted it in here. Then we had to square it, distribute it all here. Then we had to subtract the original equation because we'd substitute x into it. We crossed a bunch of stuff out. Then we were able to pull out an h, put 0 in for h, and so we got our derivative. And all that was worked out just fine. It was just kind of a long process. So eventually enough people started doing this over and over, and so they started to notice a pattern with what was originally in the equation and what turned out in our derivative. So what they started to notice is if you took the exponent times the number in front and then subtracted 1 from the exponent, we end up with the first part of our derivative. So 2 times 5 is 10, and then we just have x to the first power. And then they noticed that if you just had an x with the original number, or the x with the original term, then its derivative was just the coefficient. And then they also noticed that if you started with 3 terms, your derivative was just 2 terms. So that means the derivative of a number must just go away. So then what they did was they created something called the power rule to kind of shorten the process. You're still able to find derivatives, but you just have to do it with the power rule, and it shortens it up. So that's what this next page is showing. So let me go step by step here. So, like I said, this is the main part of the power rule. We have kind of 3 variations of it just because it takes care of some of the other special cases. So this is the main part. What we do to take the derivative of something raised to an exponent of a number is you take whatever the exponent is times the number that's in front, and then you can subtract 1 from the exponent. So for instance, if we have 3x to the 4th, we're going to take the 4 and multiply it to the number that's in front, so that would be 12, and then subtract 1 from the exponent. So the derivative of 3x to the 4th is 12x to the 3rd. So if you notice, the highest exponent I gave you to solve out using the limit definition was a cube. The reason why I did that is not because we couldn't do higher exponents, just because it was a little, once you get into higher exponents, it's really hard to multiply the x plus h's a lot. So I only made you do up to the 3rd power, but now with this power rule, it allows us to do much bigger exponents. So there's the main part of the power rule. So then the 2nd and 3rd part of the power rule kind of takes care of some of our special cases. It's what happens if there's just an x. So like I said, technically, if you remember, if there's no exponent, there's a 1. So to do the power rule, we take that 1 times the number in front, so that's just going to be the number in front. And then if we subtract 1 from 1, it's 0, so that's what I have covered up here. We never write it like this, but that's technically what happens here. We take the 1 times the a, so we have a, and then we subtract 1 from 1, so we get x to the 0, so we usually just leave that off. So that's why the derivative of a number with x is just whatever that number is with x. So if you look at our mini example over here, the derivative of 3x is going to be 3. Okay? So that's the reason why we have that first special case. Like I said, we don't typically write it as x to the 0 power. I'll leave that showing for now. So then the 3rd special case, or the 3rd part of the power rule, the 2nd special case, is what happens if you're taking the derivative of a number. Okay? The derivative of any number is actually going to be 0, and it actually kind of stems from this 2nd part of the power rule here. Because remember, it's kind of like any number has an x to the 0 power next to it, and so the exponent would be 0. So if you take the exponent times the number that's in front, well, 0 times anything is 0. So the big thing to take away from that is if you're coming upon a part of the equation, if it's a number, the derivative of 5 is going to be 0, and that's the derivative of any number. So those are the kind of the 3 breakdowns of the power rule. Like I said, the first part is the main part of the power rule, and then we had 2 special cases to kind of cover those 2 things. So The next thing is a couple more rules, and they look kind of big and scary, but they essentially just allow us to take the derivative of an equation that has multiple terms. So like I said, this is kind of big and scary, but it's just different notation because I try to show you the rules first before I actually show you an example. So with this one, basically what it's saying is that whatever terms you have added together, you can just take the derivative of each individual term. So we're going to use the power rule on both of the pieces of the equation individually. So this one, the 2 is going to be multiplied to the number in front, which if there is none, it's 1, so 2 times 1 is 2. Then we subtract 1 from the exponent, so that's going to be 2x. And then the derivative of 2x, again, if it's just a single x, the derivative of that is going to be 2. So that's why the derivative of that is 2x minus 2. So like I said, it's kind of a big, scary looking rule with all the brackets and the parentheses and this, all that. But again, that rule allows us to take the derivative of each individual term using the power rule on each term. So then the second one is very similar. What it does is it allows us the same idea. If the terms are being subtracted, then we just take the derivative of each individual term as they're being subtracted. So for the instance, for this example, if I have x to the third power minus 5x, I can take the derivative of x to the third power, so it's going to become 3 in front, because again, you multiply the exponent to the number in front, which is just 3, and then subtract 1 from the exponent, so we have 3x to the second, and then the derivative of negative 5x is negative 5. So that's why the derivative of x to the third power minus 5x is 3x squared minus 5, because we took 3 times 1 in front, which is 3, subtracted 1 from the exponent, there's our 2, and the derivative of negative 5x is negative 5. And then this third part of this rule, we've actually kind of done a little bit because I showed you that in my mini example. Essentially what it does is it takes care of what happens if there's a number in front of the variable already. We'll just multiply the exponent to it and then subtract 1 from the exponent. So the derivative of 2x to the fourth is 8x to the third. So like I said, those are big and scary rules, but all it does is allow us to be able to take the derivative of each individual term in your equation using the power rule. Okay. So then our next slide, we just have some more examples. Again, just a reminder, I talked about this the first day we talked about a derivative, but there's a couple different vocab words. A lot of times the book says differentiate. When you see that word, it just means find the derivative. So we're going to take this equation and find the derivative of each individual piece. And I do like the labels, so I use f of x a lot, but again, if it's a g of x or a y or h of x, just make sure you put a little apostrophe next to it or a prime to label that it's the derivative. So the derivative of 5x to the third is going to be 15x squared, the derivative of 3x is going to be 3, and the derivative of 5 is going to be 0. So that's why the derivative is 15x squared plus 3, because we take 3 times 5, which is 15, subtract 1 from the exponent, there's our 2, and then the derivative of 3x is just 3, because remember, if the derivative, or if the term just has a number and an x, there's like a 1 there, and then 1 times 3 is 3, and then subtract 1 from that 1, you get 0, so the x can go away, and the derivative of a plain number is 0. Could you put plus 0 next to the 3? Sure. Do we usually? No, so just leave it off. So usually, if you have in your original equation a number, your derivative should be one less term. Now like this one, we're going to have 3 parts of our derivative because we have no number. So when we take the derivative of this, again, we take the exponent times the number in front, so 4 times 4 is 16, subtract 1 from the exponent, there's our 3. Then we take 3 times 5, which is 15, subtract 1 from our exponent, there's our 2. And then take 2 times the number in front, which if there's nothing, there's a 1. So 2 times negative 2, or negative 1 is negative 2, subtract 1 from our exponent. Again, we don't typically write the 1 as an exponent. So there's our derivative. So it really does simplify the process, and it allows you to take the derivative of much larger equations much easier, because if I tried to give you something like this where you had 3 different places to plug in the x and you had to take it times itself 4 times or 3 times, that gets a little bit tedious. So that allows us to do a little bit more. So then the other thing we did was we wrote an equation for a tangent line. So it took us a little bit to find the slope, and then once you find the slope, you need the y1, the x1. So using the power rule now, we can simplify that process again. So I'm going to give you an equation and an a value, and just like before, the a value is always the x1. So we already know one part of our formula. We just need to find the m and the y1. Okay, finding the y1 is the same as before, but finding the slope is a little bit more simple. So we're going to start with the slope. So the first thing is you do is find the derivative of this. So that's where the 6x squared plus 2 comes in. Because again, you take the 3 times the 2, which is 6, subtract 1 from the exponent, there's our squared, and then we add 2, so there's our derivative. So that's the first step. Second step is we need to find the actual slope, okay? Because remember, whenever you're finding a derivative, what you're doing is you're finding a slope. You're just finding an overall slope for this entire curve, okay? So usually when I ask you to find the derivative, you're finding the slope for the entire curve. Now I'm specifically wanting the slope at 2, so the second part of it is to take the a value and substitute it into the derivative that we just found using the power rule to find my specific slope. So I'm going to put 2 in for this x. So 2 squared is 4, 4 times 6 is 24, plus 2 is 26. So there's my slope. So I have my x1 and my slope. So now just a quick reminder of how you get the y1. Since this is my x1, to find the y that's attached to this x, you just need to substitute it into the original equation. So to find y1, we're going to take the a value and plug it into my function. So that's what I'm showing here. So we have 2 to the third power times 2 plus 2 times 2 minus 1. So 2 to the third power is 8. 8 times 2 is 16. And then this would be 4. So 16 plus 4 is 20 minus 1 is 19. So we have our point and we have our slope. So now the last thing is just to substitute it into our formula and find the equation. So this is step 4. I couldn't fit it down here below, so we're going to go up here. So we have our y minus our y1, which is 19, equals our slope, which is 26, times x minus x2. And then, as always, we simplify. So I distributed the 26 into the parentheses. So I have y minus 19 equals 26x minus 52. And the last thing is take that 19 and add it over to the 52. So our final equation is y equals 26x minus 33. So again, you know you need to do that whenever it says write an equation of a tangent line, or anytime it says equation. That's really the important word you look for when you know you need to write something like this. So like I said, that's something we've done before. Now with the power rule, it simplifies the process. Alright, now that we know the power rule, we can actually now involve other exponents. So with this one, we used this a little bit at the beginning of the year when we did our review chapter. Whenever you have a root changes into an exponent. So the exponent comes from the root that's in front of it, the little index here, and then the number that's with x. So if you have x to the, this is the square root of x cubed, then we do x to the 3/2 power. So it's always the fraction exponent that comes from inside over out is one thing I say. So what we can do is we use the power with square roots or any type of root. So we change the, rewrite the equation into a root form, and then we can use the power rule. So take the exponent times the number in front, subtract 1 from that exponent. So here, and I kind of already jotted stuff in because, like I said, my board wasn't quite working, so you can kind of see it. So this is a square root. So remember, if there's no number in front of the root, that's 2 because it's a square root, and if there's no number with no exponent with x, it's a 1. So what we did first is rewrite into this exponential form. Okay, so we have x to the 1/2 power, and then that's what we end up taking the derivative of. Okay, common mistake, some people do the rewrite step and then they forget to take the derivative. So all we've done is taken this from root form into exponential form, and so now let's find the derivative. So we take 1/2 times the number in front, and then we subtract 1 from the exponent. Okay, going to go ahead and show you the answer here real quick, and then I'll come back to how we got it. So I take 1/2 times the number in front, so that's where the 1/2 comes from, and then we still subtract 1 from the exponent. So if we take 1/2 minus 1, we actually get negative 1/2. Okay, hopefully that makes sense, because if you're taking a half and you're subtracting 1 from it, it goes back down to a negative half. Where that actually comes from is common denominators, as always, when you subtract with a fraction. So if you have 1/2 minus 1, really you put 1 over 1, and then you can make it a common denominator, so it's 2 over 2. So then 1/2 minus 2 over 2. Again, once you have the common denominator, that is your denominator, and then you subtract 1 minus 2, there's our negative 1. So that's how you get that exponent. Okay. So now over here, just kind of a different variety. We can have numbers in front of roots, that's fine, that's going to just stay in front of it. And so then we have, this is the cube root of x squared. So first we rewrite it. So this becomes 2x to the 2/3. Okay? Again, if there's a number in front, it just stays there. We're just going to take the root into exponential form. So then just like before, we multiply. So if you take 2/3 times 2, remember, think of it as like 2 over 1, and when you multiply fractions, you just have to multiply straight across. So if you have 2/3 times 2, that's going to become 4/3. Start showing my answer here. And so then we have x, and then the exponent we're going to give to x, again, we have to subtract 1 from the 2/3. So again, we have to make a common denominator. Get my boxes out of my way. So that's going to become 3/3, so then 2/3 minus 3/3 is our negative 1/3. We are going to end up using quite a few exponents. We're going to get really good with our exponent rules again. I do want to make a couple of notes with this. The exponent will, if we're working with fractions, will remain a fraction. Do not change it into a decimal, and also leave it as an improper fraction if it happens to be one. So no mixed numbers as exponents. So like this one I left as 4/3. Usually I leave all my fractions as mixed numbers, or as improper fractions instead of mixed numbers. So again, just make sure that we have our fraction as our exponent. So if it happened to have been like 5/3, leave it as 5/3. Don't change it to 2 and 2/3, or 1 and 2/3, sorry. So again, leave everything as a fraction as an exponent, and if it's improper, leave it that way. So now another exponent that we can use, another exponent rule that we haven't used for a while that we can use, is a negative exponent rule. Okay? We actually end up using this rule in reverse, because if something's in this format where it's x to the negative exponent, we can use the power rule, but if it's in this format where it's a fraction, we can't. So what we do is, if we have a number over x to an exponent, we can take it and rewrite it as a negative exponent so that we can use the power rule. So we're going to reverse the fraction into just an exponent, and when we do that, if we take something out of the bottom of a fraction, if we just make its exponent negative, we can take it out of the bottom of a fraction. So for instance, with this first one, 1 over x to the 8th, we're going to take the x to the 8th and we're going to move it up top with the 1. So the way we can move it up top with the 1 is by making the 8 negative. So we're going to take this 1 over x to the 8th and rewrite it as 1x to the negative 8th. Now, would you have to necessarily write the 1? No. But that's just kind of emphasize that if there is a number up here, it stays. What we're essentially doing is just moving this x to the 8th up with it using a negative exponent. So now that we have it in this format, we can use our power rule to solve it out. So we're going to take negative 8 times the 1 and then subtract 1 from the exponent. Do make sure you're careful here, though. We are subtracting now with negatives. So if we take 8 times negative 1, or sorry, negative 8 times 1 is negative 8. And then if we subtract 1 from 8, that's negative 9. So always make sure you're watching your negatives. So then for our second example, we have 4x to the 3rd. And so again, the x to the 3rd is going to move up with the 4. And then the x to the 3rd, instead of being to the positive 3rd, it's now going to be to the negative 3rd. And so now we can take the and use the power rule with this. So we take negative 3 times 4 and then subtract 1 from my exponent. So I end up with negative 12x to the negative 4th. So that's another exponent rule that we can use. Okay, so let's do another example where we kind of combined everything. So, 2x to the fourth was fine, so we're just going to leave that. But before we take the derivative, we need to switch this middle term to 3x to the negative second, and this last term to its fraction exponent. So here I took it and rewrote it. So 2x to the fourth didn't change, 3x to the negative second, so that we can use the power rule, and then this became x to the 2/3 power. Again, I'm emphasizing again labels. I do want you to label it with the dot notation. So this is still the regular function. I haven't taken the derivative yet, so that's why I just left 2x to the fourth the same. The common mistake is some people, if you start doing the derivative on a part that you already can and not on the other part, then you actually accidentally forget to do the derivative. So again, still like before, we're going to do our power rule. So this term, we took our exponent times our 2, so that's our 8, subtracted 1 from it, so there's our 3. Took our exponent times our number in front, so negative 2 times 3 is negative 6, so we changed that sign, subtracted 1 from that, so we got negative 3. And then here again I'm showing the fraction work here. So I took 2 times 2/3 times the negative 1, so that's negative 2/3, and then I subtracted 1 from the exponent, so I had to make a common denominator here. So 2 minus 3 is that negative 1, and so we keep the same denominator, so it's negative 1/3. So I know fractions can be a little bit tricky, but again, we're still just using the power rule. So hopefully all that made sense. Oh wait, so the next thing that we're going to talk about is kind of unique, because once we have the power rule, it really kind of simplifies our process, so then we can do more with it. So we can write equations for tangent lines easier, we can take derivatives of bigger functions. The other thing we can do with it is actually, now that we know the power rule, is we can take derivatives of derivatives. And so that's what higher order derivatives is called. Okay, so just a little bit of notation here first. So again, first derivative has the prime. Again, I'm trying to still emphasize because the book likes to use the dx notation. So I also have that with it. So that way if you see it in the book, you know what it's talking about. So second derivative, with the dot notation, just put two apostrophes there. If it's in the ddx notation, you'll see a little exponent of 2, also meaning just take, so once you find the first derivative, take the derivative again by using the power rule one more time. Third derivative works out the same. So again, once you've taken the first and second derivative, just use the power rule and take the derivative again. So if it's in the dot notation, do 3 dots. If it's the ddx notation, you'll see a little 3 there. And then once, for some reason, once they got to 3 with the prime notation, they also started switching to 4, because the more apostrophes you get, the harder it is to kind of read. So once you get to the fourth derivative, it's just a little 4. That means you're going to take 4 derivatives. Now you can't just skip to that whatever derivative I ask you for. You actually do still have to take the derivatives in between, which should make sense. But again, that's one thing to look for, and we can actually do that indefinitely. You can find an infinite number of derivatives. Typically, we stop when it's 0, because once you hit 0, the next however many derivatives are going to be 0, because the derivative of 0 is 0. So you can continue on past that. So say I wanted you to find the 8th derivative, and the 6th derivative was 0. Well, that means the 7th derivative is 0, the 8th derivative is 0, so it's going to be 0. So that's typically why we tend to stop once we hit 0, but that doesn't mean we can't go past it. Alright, so here we're going to compute as many derivatives as we can until we hit 0. Most of the time the way I format this is I actually tell you how many derivatives to compute, but just to kind of get the hang of it, be able to take as many derivatives as we can until we hit 0. So our first equation is 4x to the 6 plus 5x squared minus 3. So its first derivative, we took the 6 times 4 is 24, subtract 1 from the exponent, there's our 5. Take 2 times the 5, which is 10, subtract 1 from our exponent, which is 1, and the derivative of negative 3 is 0. So there's our first derivative. Second derivative, do that same thing again. We're going to take 5 times 24, which is 120, subtract 1 from our exponent, there's our 4. The derivative of 10x is just 10. So there's our second derivative. Third derivative, take the 4 times 120, that is 480. Subtract 1 from the exponent. There's our 3. The derivative of 10 is 0, so we leave it off. So then we can keep going. So the fourth derivative, take 3 times 480, which is 1,440. Subtract 1 from our exponent. There's our 2 as our exponent, so there's the fourth derivative. Take another derivative, take the 2 times the 1440, so you get 2880. Again, our exponent is now 1, so there's our fifth derivative. Okay. Then I ran out of space, so I moved up here. So our sixth derivative, again, if it's just a number with x, it's the number, so it's 2880, so there's our sixth derivative. So we can actually go one more time, because the derivative of 2880 is going to be 0. So we can stop at 7, but like I said, the 8th derivative would be 0, the 9th derivative would be 0, the 20th derivative would be 0. So eventually we hit a stopping point when we have exponents like this. If we're working with negative exponents or fractional exponents, we can actually continue indefinitely and we will never hit 0. So I'll only ask you to do this with ones that you can actually hit 0. But again, once we hit that 0, we're going to stop. So this one took 7 derivatives to do that. And usually it's one more than the biggest exponent, to give you a helpful hint. So like I said, usually I format it as actually giving you a definitive, okay, I want you to find the fourth derivative or the fifth derivative. This time I just wanted to do that until we get hit 0. Okay, so we've done the power rule, several variations of it. We wrote equations for tangent lines. We did higher order derivatives. And the last thing we can apply to this is velocity, just like we've been doing with our other definition. So just to run through this real quick. So typically, when we're talking about physics or velocity and positions and objects moving, we call the position function s of t. I don't know why we use an s, but the t is for time. So that's our starting position of the object. So that's going to map how the object moves. Okay, if you take the first derivative of that, that gets you velocity. And now that we know a little bit about higher order derivatives, actually the derivative of the velocity, or the second derivative of the position function, is acceleration. So you take the derivative, the first derivative is your velocity, the second derivative is the acceleration. So when you're asked to find instantaneous velocity, first derivative, instantaneous acceleration, second derivative. So you still might just be asked to find one, but sometimes you're asked to find both. So again, just take the derivative of your derivative to find the acceleration. So let's do some examples, and make sure you label. So for these next couple examples, we're just going to find instantaneous velocity or acceleration. So you should have your note packet, so I'll just kind of read through this. So this is a height of a falling object given by this position function in feet. We're finding just the instantaneous velocity at 2. So what we have to do with this one is we can use the power rule with our position function to find the overall derivative. And then since we want to find a specific velocity, once we find the derivative, plug the 2 in for our specific velocity. This one's not asking us to do anything with acceleration, so we just have to worry about velocity. So first thing we do, take the derivative of our position. So derivative 64 is going to go away because it's a number. Take 2 times the negative 16 is negative 32. Don't forget your negative. And then subtract 1 from our exponent, so our exponent is just 1. So there's our overall velocity for that entire function. Okay. So now we're going to specifically find the velocity after 2 seconds. So what do we do with that 2? We plug it in for t. So you take negative 32 times 2. Well, that's going to be negative 64. And since we're talking about velocity, it's feet per second. So that really does quicken up that process of velocity. Okay? So, like I said, you just kind of have to pay attention. Sometimes, if you're just asked to find the instantaneous velocity and they don't give you a value, your answer is just going to be the derivative. Here we're finding instantaneous velocity at a specific value. So once you find the derivative, plug in that number to find that specific velocity. So like, for example, for this next equation, or next example, we're talking about a skydiver jumping out of an airplane. This is his the map of how he's falling, okay? So we're just asked to find the instantaneous velocity and the acceleration. Notice there's no t value So that means our answer is just going to be whatever the derivative is. So we're going to find a general velocity and a general acceleration for this problem. So we're not always asked to find a specific velocity. So we do have to do both. We do have to find velocity and acceleration. So to find our velocity, again, just an overall general velocity is just take the derivative. So the derivative of 820 is 0. The derivative of negative 15t is negative 15. The derivative of negative 16t squared, take the 2 times the negative 16 is negative 32. Subtract 1 from our exponent, and it is still velocity, even though it's not a specific velocity, I do want to label. So it's feet per second. Okay? And then finally, it's also asking us to find the acceleration. So we'll take whatever our velocity equation is and take its derivative. So the derivative of 15 is going to be 0. So the derivative of negative 32t is just negative 32. So this time, our acceleration, no matter what, is negative 32. And since this is acceleration, it's feet per second second, or feet per second squared. And that's how you find acceleration really easily. So I hope this worked okay. Like I said, my Promethean board is just kind of acting up. So hopefully just being able to hear me and kind of seeing my mouse move was helpful enough. Again, let me know if you have any questions. If my Promethean board still continues to act up, I may end up having you maybe get on Zoom. But you should now know how to do each problem from the assignment. Like I said, with these, it's a mixture of just power rule. So if it says differentiate, it's just asking you to find the first derivative. That's it. Then if it wants you to find more derivatives, it'll tell you. There's some velocity questions. Again, sometimes you might just do general velocity. So you just find the equation for the velocity, or sometimes you might be asked to find the specific velocity. So once you find the derivative, plug the number in, and you're looking for that specific velocity. And there are also a couple equations, or where you're going to write the equation of a tangent line. So hopefully this was helpful, and again, please let me know if you have any questions. Right now.